Okay, so in the last example we finished here and we were looking at solutions to the differential equation, and today I wanted to talk mostly about something that doesn't really belong in this section explicitly, and that is a different way of solving for a differential equation. It's solving a DE by substitution. And the substitutions I will typically be giving you, you'll remember that this was what a homogeneous differential equation was, right? Homogeneous DE. That was a differential equation of the form y prime equals f of y over x, meaning wherever you see a variable, you could write it as y over x. Okay, and do you remember what we did? We solved by taking w equal to, I guess it was v equal to y over x, and then we found a formula for v prime, and then we found a formula for y prime in terms of v prime, and so we made the substitution into the differential equation and we were able to solve it that way. Today we're going to be looking at differential equations of the form y prime plus p of t, p of t times y equals g of t times y to the nth power. And these differential equations are going to be called Bernoulli. These are Bernoulli DEs. And these can be solved by using a substitution. Use a substitution. How many T's are in substitution? Okay. Use a substitution to solve. Okay, I do know how to solve substitution. Okay, so how is this going to work? You divide by y to the n power. So this, by the way, just to emphasize, this is the nth power, not the nth derivative, right? So if I divide everything, I get 1 over y to the n, y prime, plus p of t times y over y to the n is equal to g of t. Okay, now remember this is y to the minus n power, y prime plus p of t times y to the n minus 1 power is equal to g of t. Okay, and we will substitute, let's say w maybe. W equals y to the n minus 1 power. Oops, let me not put that in brackets like that because that's confusing. I see I made an error there anyway. That's 1 minus n, right? Did you guys catch that? Okay, so if I'm going to substitute, so this is y w of x, or w of t I guess in this case, is equal to, this is y to the 1 minus nth power, and that's evaluated at t. Okay, now I need to substitute something in for this expression. So if I differentiate both sides of this, what do I get? dw dt equals 1 minus n times y to the 1 minus n minus 1, right? And so the minus 1 and the 1 cancels, and what do we get? Oops, let me move this over. I'm differentiating with respect to t, right? So if I have a function raised to a power, let me have a side note here. Side note. If I'm differentiating like f of x cubed, how would I do that? That would be 3 times f of x squared, but then you have to multiply by f prime of x, right? By the chain rule. And so the same thing here, I have to multiply this by dy over dt. And on this side then, what do we see we have here? I think you might see that we have, I'll put it in red here, this is the same thing as this. Okay, and this is the same thing as this. So let's see if I can rewrite this now. dy over dt times y prime is equal to 1 over this times this, so this is going to be 1 over 1 minus n times dw over dt plus p of t times w of t equals g of t. And what do you see here? This is linear in w. Okay, and so therefore we can solve it. Solve for w, and then once you have w of t, right, then you can solve for y of t after that. Now notice that all of this works as long as n is not equal to 1, right? Does that make sense? Why that would be? Because what happens if n is equal to 1? Here's the original differential equation. If n was equal to 1, then you could bring these together, right? And then you would have just y prime plus something times y equals 0. Okay, so the equation, the original equation, would be linear if n is equal to 1. Good. Okay, now let's see if we can solve an example problem like that. So example about y prime plus 4 over t times y is equal to t cubed y squared. Okay, so if I divide by y squared, I get 1 over y squared y prime plus 4 over t times 1 over y equals t cubed. And now our w is going to be 1 over y, or y to the minus 1 power. So dw over dt will be y to the minus 2 power, right? Then I'll have to have a minus 1/2 here. Good. Oops, I anti-differentiated. Did everybody catch that? I'll erase it real fast. So this should be minus y to the minus 2. Okay, there we go. That's the derivative. Oh, times y prime. I almost forgot that. Okay, so the idea here is that minus w prime is equal to y to the minus 2 y prime. And so I can substitute here. Oops, I tried to get a different color. Here to here. Right, so I now have minus w prime plus 4 over t times w equals t cubed. Okay, and now I multiply through by my minus 1. Good, and now we can solve by integrating factor. Oops. That's going to be e to the minus 4 times the natural log of t equals t to the 4th, minus 4th, or 1 over t, 1 over t to the 4th. Good. So w over t to the 4th prime is equal to minus 1 over t. We're getting there. So now we can integrate. Good. That's going to be minus natural log of t plus c. So finally w is minus t to the 4th natural log of t plus c t to the 4th. But we're not finished yet, because w is equal to what? 1 over y. So we have 1 over y is equal to minus t to the 4th natural log of t plus c t to the 4th. And so then we could just write y. 1 over minus t to the 4th natural log of t plus c to the t to the 4th. Good. There we go. That's not too bad. So give the other ones a try. They're very similar. Again, the idea here is for Bernoulli equations, we have the form where we have, let's see where it is. There it is. We have this form starting off. And it almost looks like a linear differential equation, except you have a y to the nth power sitting over here. And so the idea here is that if you divide by y over n, then this is what you want to substitute. Okay, and if you do, then you'll automatically get this piece for your derivative, and then you'll get a linear DE out of that you'll be able to solve for W. And then finally, at the very end, back substitute, put in your y again, and that's it. Bernoulli equations are kind of fun to solve. Yeah, because sometimes things are either Bernoulli or something else, and sometimes Bernoulli is the easier way to go to solve. So I will leave it there, and I will see you in the next section.